Hello, my name is Rima Daher, and today I will be presenting the paper titled Towards Richer 3D Reference Maps in Urban Scenes, along with my colleague Maya Antoun. The authors of this paper include Maya Antoun, Dr. Daniel Asmar, and myself, Rima Daher. We are all part of the Vision and Robotics Lab of the Mechanical Engineering Department in the American University of Beirut. To lay down the outline, we will first start with the introduction, followed by the related work and paper contributions. We will then move to the proposed system and the experiments. Finally, we'll present our results and acknowledgements. In this work, we proposed a first step towards automated reference maps by mapping cars in 3D and localizing them in a metric map. The cars are represented by meshed hypersurfaces with close resemblance to reality. The cars are drawn at the correct scale, position, and orientation. As a byproduct, the resulting semantic map has a potential to improve vehicle localization under the framework of SLAM. The created reference map has detailed information about the studied environment and can be used for different applications, such as those in augmented reality, virtual reality, and intelligent transportation systems, like smart parking, statistical surveying, urban planning, traffic management, and marketing. In the literature, objects are included in some systems to enhance localization of SLAM only, whereas others are also concerned with mapping. These are the systems we compare our maps to, and they are represented in three groups. The first group represents objects in the map as geometric shapes and quadrics, which is not semantically significant. The second group represents objects using a prior model where one template is used to represent the detected objects in the map. Finally, the third group represents objects by completing their shape based on quadrics and not on the incomplete object point cloud, which we will be doing in our system. Another downside of the system is that after reconstruction, scale is lost and post-processing is required. The contribution of this paper include introducing a method to produce maps with 3D objects portrayed in their true shape and their correct metric pose, to improve to what has been shown in the literature. Another contribution is that the car shapes are optimized when their meshes are complete. Their 3D position is better estimated and the final localization is improved. In this slide, we can see the flowchart of our proposed system. First, StereoSLAM produces keyframes and a feature map. In each keyframe, cars are detected using fast RCNN and delineated both in 2D and 3D using 3DOP. To complete each car shape, its missing parts are hallucinated and meshed using shape priors. The resulting optimized centroid is used as a feature in a separate optimization to improve the camera pose. For the optimization, data association is performed in 3D to avoid the 2D occlusion problem. The optimization problem is solved using Levenberg Marquardt. Finally, the complete car meshes are inserted into the 3D map at their optimized centroid locations, creating a more meaningful map.
Moving to the experiments. To validate our system, we tested on the stereo images from sequence 00 of the Kitty odometry dataset. OrbSLAM2 is used to perform StereoSLAM, where 1,600 images are inputted to complete one loop of the car's trajectory. Then 512 keyframes are extracted from this sequence and used by 3D object proposal to generate 2D and 3D proposals of cars. Next, these proposals are fed into a pre-trained fast RCNN detection network, where 2D and 3D bounding boxes of the detected cars are marked. In their native form, the shapes of the segmented cars are not fully completed and are therefore processed by shape priors to complete them. The centroids of the completed cars are then transformed to the word frame using OrbSLAM2 transformations. For the optimization, K nearest neighbor is used to find the correspondences between centroids belonging to the same car from different keyframes. Moving to the results, we compared our system map with other systems. As you can see in the figure, in OrbSlam2, the generated map only includes orb feature points that are not semantically meaningful. Whereas in CubeSlam, the semantic map includes cars that are only represented by one template. Therefore, all different cars have the same shape and size. Moving on to the system presented by Hossein Zadeh, the car shapes are completed based on bounding quadric and not based on the real car shape. This completion does not generate cars similar to their real shapes. On the other hand, the results of our system show a more aesthetically meaningful map than the others. This is partly due to representing cars with different shapes and sizes through completing their shapes based on not only the bounding box or quadric, but also on the segmented car point cloud. Another reason is that a point cloud with texture from the segmented stereo reconstructed image is also added to every car. The net result is a map with more realistically looking car. Having more accurate maps, metrically and visually, makes them useful in their current state without any post-processing. As a byproduct, our system is capable to improve the localization in SLAM. In our experiment, outliers were detected and were removed by setting different criteria for detecting cars that include a depth limitation factors, where cars deeper than this factor were not accurately represented. This is due to the sparsity of point cloud in the stereo reconstruction at high depth values. Due to this reason, a point count limitation for shape completion was also set. Another criteria was a probability threshold for the detection network. Finally, a manual verification of car poses was done. This figure shows the car trajectories before in red and after removing wrong detections in black. It is apparent from this plot that wrong detections caused various outliers in the trajectory. Consequently, these outliers negatively affected the entire estimated path of the camera. In addition, we can see the clear improvement in the trajectory estimate from our proposed system in black versus that of OrbSlam2 in cyan. As for the numerical evaluation, we can see that our system was able to reach an average relative translation error of 0.62% compared to 0.70% in OrbSlam2. Finally, the authors would like to acknowledge the American University of Beirut, AUB, and the National Council of Scientific Research of Lebanon, CNRSL, for granting a doctoral fellowship to Maya Antoun. Thank you.